All right, we are going to move into our next unit here, and as we had before, there will be a couple of assignments based on these. Okay, I'm sure you've seen this before, but let's roll through a little bit of the scientific method. There are two types of observations we make. Quantitative, those involve numbers and units. An example would be like number of students in a room. And qualitative, those involve categorical data, and an example here would be like what color shirt you're wearing. Great. So if we're formulating a hypothesis and performing an experiment, we need to talk about data gathering. When you have a quantitative observation, you'll have a number and a unit. Like these examples, 20 grams and 6.63 times 10 to the negative 34th joule seconds. Here are some units and their abbreviations. Some of these we will use like mass, length, temperature, and some of them we will not use like candelas. Now this is a confusing slide. This is just to show you how many units we can get from just the base units on the left. These are the most useful SI prefixes. A prefix is something that just goes before the unit. So here we could talk about kilograms, and those would be 10 to the third grams, or 1,000 grams. We will talk about centimeters and millimeters, which are hundredth and thousandth of a meter. Here we can talk a little about uncertainty and error, and how there will always be uncertainty in every measurement. Basically, since there isn't an instrument in the world that can measure to an infinite number of decimal places, the next digit will always be uncertain. This brings us right to accuracy and precision. Sometimes people use these synonymously, but they don't actually mean the same thing. Here are the two definitions for those, and as you can see, the first picture is very accurate because they're aiming for the middle and they hit the middle. But it's also precise because all three shots hit in the same area. But this middle picture would not be considered accurate because they didn't hit the middle. However, it is considered precise because all three shots are in the same area. And the right picture here is just trash. Neither accurate nor precise. Last little bit here, there are basically two types of error. Random error means it can be higher or lower, something random happened, and you have no way of determining how it messed you up. But systematic error will result in the same direction of error each time. Let me give you an example of this. So if you're weighing things on a balance and you forget to zero out the weigh boat, then your sample will always weigh more than it should. And here's another example. If you are required to dry something out, but you weighed it accidentally wet, it will always weigh more than it should, and this will throw off your results, and that's not what we want. All right, so in chemistry, we got to talk about significant figures, or Sig Figs. It's a way to determine what the important part of a number is, and there are rules for it. Rule number 1, non-zero numbers always count. So the number 3,456 has 4 Sig Figs. We are counting the number of digits. So we're counting 1, 2, 3, 4. All of those digits are significant. Rule number 2, leading zeros do not count as significant. This means any zeros that is in front of a number is not significant. So this number, 0.0486, has only 3 Sig Figs, the 4, the 8, and the 6. The zeros do not count as significant. Rule 3, captive zeros always count. What I mean by captive is between two numbers. So this zero does count, and this number 16.07 has 4 Sig Figs. 1, 2, 3, and 4. Last rule here, trailing zeros, or zeros at the end of a number, are only significant if the number has a decimal point. So this number, 9.300, has 4 sig figs. 1, 2, 3, and 4. There are also some exact numbers that actually have an infinite number of sig figs. So like the conversion between inches and centimeters is exactly 2.54. This does not mean it has 3 sig figs, it means it has an infinite number of sig figs. Alright, here are some examples for determining sig figs. And if I were you, I would pause the video here and try to work these out on my own to make sure I understand the concept. So these zeros are captive, so they do count. We count each digit as significant. 1, 2, 3, 4, 5. So this has 5 sig figs. This has a 0 at the end with a decimal point, so it counts. So it has 4 sig figs. 1, 2, 3, 4. This one might be tough. 2 captive zeros count, but the one at the end does not. It only has 5 sig figs. 1, 2, 3, 4, and 5. This actually has all numbers here. The times 10 to the third is just adding zeros at the end, so it doesn't change the numbers. This has 3 sig figs. And finally, all zeros in the front of this one, those are not significant, so this only has 2 sig figs. Oh, I missed one last one here. All zeros at the end are not significant, so this only has 2 sig figs. All right, so we can actually do math with these as well, and they have different rules for what you're trying to do with it. So for multiplication or division, you can only use the same number of sig figs as the number with the least number of sig figs that you're using in the calculation. Let me explain what that means. So we have this calculation, 6.38 times 2.0. If you plug that into a calculator, you get 12.76. Great. But the rule for sig figs is that you can only use 2 sig figs in your answer because of the 2 numbers you used. 6.38 has 3 sig figs and 2.0 only has 2 sig figs. Now this poses kind of a problem. We get an answer of 12.76, but we have to round our answer to only 2 sig figs. So basically we're going to count 1, 2, we have to decide to round the second digit, which is the 2, and we look to the next digit to figure out whether we round that up or down. So because it's a 7, which is more than 5, we round it up and we make that 2 into a 3. And our final answer becomes 13. Okay, here is a bunch of practice on this. And I really encourage you to pause the video and use the calculator either on your phone or the laptop to really calculate these numbers. Then you'll round them based on the number of sig figs. Okay, so we have 3.24 times 7.0, and the calculator gives us 22.68, but we can't have that many sig figs. We can only have 2 sig figs. So we have to round our second digit, and we get 23 as our answer. If we try to divide 100.0 by 23.7, and at some point in this class you probably will ask me how many digits to round to, but the answer is that we follow sig figs. So the rule here says that we can only have 3 sig figs in our answer. So we round this to 4.22. Now this might be a tough one. The 2 numbers we have is 0.02 and 2.371. The least number of sig figs is 0.02 with only 1 sig fig. So we write out the calculator answer, and then we round it to 1 sig fig, which is 0.05. Okay, we can only have 2 sig figs here, so we round this one to 240. And 3 sig figs here, so we round this to 5,870. 3 sig figs here, so we round this one to 2.96. And finally, we have 3 sig figs here, so we'll round this one to 2.96. Now, if we're adding or subtracting, we use a different rule. This rule is all about the number of decimal places. So if we're using these two numbers, 6.8 and 11.934, we use the same number of decimal places in our answer as the one with the least number of decimal places. So instead of 18.734, we have to round it down to 18.7 because we can only use one decimal place in our answer. And again, I encourage you to really pause the video and take practice in this because practice is the mother of skill. Okay, if we add these together, we would get 10.24, but we're only able to use one decimal place because of the 7.0, so we have to round that down to 10.2. Subtracting these gets us 76.27, but we can only use one decimal place, so we get 76.3. And adding these together, we get 2.391, but we can only use two decimal places, so we round that to 2.39. Now, if you do this one on paper and line up the decimal places, you can see that we're only supposed to have one in our answer. So even though the calculator says 709.228, we round that to 709.2. Again, we are only allowed one decimal place here, so this rounds to 1,821.6. And finally, here's a weird one. We only get an answer of 0.16, but both numbers have 3 decimal places. So our answer should have 3 decimal places. So what we have to do here is actually add a 0. It doesn't change the number, but it does show the correct number of Sig Figs. All right, so in chemistry, we often deal with numbers that are so large or so small that it's hard to get past the scale of the numbers. Like all the zeros really drown out the actual important numbers. Luckily, we have a way of dealing with these numbers, and it's called scientific notation. Basically, we treat the number and the scale as two different things. So we have this equation we will use. M times 10 to the n. M will be any number between 1 and 10. M will be any number between 1 and 10. It does not have to be a whole number. It can have a decimal. And n will be any integer. It can be positive or negative. Let's just say we have a number like this. We have 4 steps in order to get it into scientific notation. Step 1. Insert an understood decimal point at the end of the number. I'm sure you guys will agree that if we put a decimal point right here, that it won't change the number, right? Step 2 is to decide where the decimal point must end up so that one number is to its left. This is your M. So basically, we're going to put the decimal point right here. Step 3 is to count how many places you bounce the decimal point, and this is your N. So we're counting how many places to get it from there to here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then all you have to do is rewrite it in the form m times 10 to the n. So the m in the example is 2.5, and you will always have a times 10, and then the n was a 9. And the 9 is a superscript which tells you how many zeros it has. This one already has a decimal point, so we can skip step 1. Go on to step 2 and decide where the decimal must end up so that one number is to its left. That means we are going to place it between the 5 and the 7. Next, you're going to count how many places you bounce the decimal point. 1, 2, 3, 4, 5. And then we rewrite it in the form m times 10 to the n. So in this example, our m is 5.79. So we write 5.79 times 10 to the negative 5th. And understand that positive exponents are for very large numbers and negative exponents are for very small numbers. Just a couple more things to know here, we're almost done. If the exponents are the same, we can actually add or subtract numbers in front and then bring the exponent down. So we would just add 4 plus 3 and bring down the exponents to give 7 times 10 to the 6th. Or we could subtract 4 minus 3 and bring down the exponent to give 1 times 10 to the 6th. But that's only if the exponents are the same. But if the exponents are not the same, we can move a decimal point to make them the same. As a rule of thumb, it's easier to move the smaller number, the one with the smaller exponent. I'll work through this real quick. So instead of 4 times 10 to the 6th, you could say a student saying, I can make the exponents the same by using 40 times 10 to the 5th. They're the same exponent, now we can just add them and I get 43 times 10 to the 5th. But this is no good because our m, the 43, is not a number between 1 and 10. So we have to move the other one. We have to move the 3 times 10 to the 5th to the left and get 0.3 times 10 to the 6th. And then it's very easy. We just add 4 and 0.3, we get 4.3 times 10 to the 6th. One last example here. If we have these two numbers, 2.37 times 10 to the 6th, and we're adding it to 3.48 times 10 to the negative 4th, and remember, we're going to change the one that's smaller. We're going to move the decimal over 2 times and get 0.0237 times 10 to the negative 4th. And adding that, we get a final answer of 3.5037 times 10 to the negative 4th. All right, so after all that, you guys are now ready for activities 3 and 4. I'll be posting those to Schoology for you. You can probably have that done and submitted back to me by Friday, September 25th. You can use VIP 6 to help you. And as always, let me know if you have any questions or problems, and thanks for watching. And 3 sig figs here, so we round this to 2.96. What? All right. We can actually do math with these as well, and they have different rules for what